Exercise 5D, log laws. Today we're learning about using log laws to solve equations. What you need to be able to do is recall logarithmic laws and apply log laws to simplify and solve equations. So of course, log laws were introduced to you in year 11, some of you maybe even year 10. But we're just going to kind of review them and then we're going to apply them to some questions. The logarithmic function has a base of a and it's defined as following. So you can see here that this is my exponential equation, a to the power of x equals y. Well, the relationship between the two is that if I want to take the base over to the other side, so the opposite of the exponential base is actually the log-based a. So that's how we can see a relationship between a and log. They're actually inverses of each other, which we'll talk about a little bit later on. So in terms of values, if you think of 2 to the power of 3 is equal to 8, so what's the opposite of that? It's kind of like saying 2 to the power of what gives me 8? Well, the answer to that will be 3. So the log poses the question of 2 to the power of what gives me this value. So that's what we mean by the opposite. And that's how we can also solve some equations where it's not as easy as just changing the base. Okay, so logs come with their own set of laws, just like our index laws, and you'll find that a lot of them feel like the opposite of our log laws. So I'll quickly run through them now. Again, you would have already looked at this, but just as a bit of a refresher. So when I've got a log of two bases, if I'm adding the logs, then I can actually multiply the inside. And think of it like the exponentials. Remember, when we have the same base and we're multiplying, then we end up adding the powers. So it's literally the opposite. When I'm adding two logs, I multiply the inside. Now, same with minus, right? When I'm minusing the two logs, then I divide the inside value. This is a really useful one. Log a m to the power of n. What you can actually do is pull that power out. So it becomes n log am, and you're going to use that one very often. Now, log a1 equals 0. Remember the question of log, right? So a to the power of what gives me 1? That would be 0. And then log AA, so if the base and the value is the same, that would be 1. Again, a to the power of 1 gives us a. So that's the question of log. Now, log A0 is undefined because there is nothing that I can ever put a value to a power of that will give me 0. So that will be undefined in that case. Log AX is defined for x being greater than 0 and for a being an element of every real value except for 1. Finally, log A to the log AM, the A and the log part kind of cancel out and it just gives you this particular value here, which is M. Okay, so hopefully all of these laws make sense and let's go ahead and define them, or not define them. We've just done that. Let's go ahead and use them. So this one says to simplify the following. Now, again, we're really thinking about how can I simplify values to be of the same base? So one of the best laws that you'll use a lot is this one, log AA equals 1. So I want to try and make these bases the same, because if I can, then I can make it to the power of 1 or equal to 1. So I'm thinking, can I rewrite 64 as a base of 4? Which I can, that's to the power of 3. 16, I can write that as 4 to the power of 2. And then 256, that would be 4 to the power of 4. Okay, so that's really, really nice. Now, the next law, which remember I said you're going to use quite often, is that if I have a power, I can actually pull that out the front like that. So I'm going to go ahead and pull all these powers out. Now, I'm only going to do it for this time. In future, I wouldn't even do that. I would just cancel that out and I would write 3. But I'm going to just do it because it's the first time. So this becomes log 3 log 4, 4, 2 log 4, 4, and I wrote this kind of weird here. Let me fix that up. Should be a base 4 to the power of, oh, I just forgot the base, that's all. So we're going to pull the 4 out. And that will be 4 to the 4. Okay, now remembering that log 4, 4, because it's the same, is just 1. So all of these values are just 1. So I end up with 3 plus 2 minus 4. So that'll be 5 minus 4, which will give you also 1. Okay, so let's try a similar thing with our next one. Now, this one is probably not necessarily as obvious because I can't write 7 as a base of 3. That's just not going to work. And I can't write 21 as a base of 3 either. But remember that if the bases are the same and we are subtracting, we can actually multiply the insides. However, I do have a value here. So first thing I'm going to do is pull that value in. And then I can go ahead and multiply the inside values. That'll be 7 squared. Oh, not multiply. Sorry, we will divide 21 squared. Now, just because if you're trying to do this by hand, and then I'm going to get you to see if you can see anything interesting. Now, remember with your index laws, AB to the power of m is the same as saying AM, BM. It's the same situation. So I'm just going to pull the 2 out. Then remembering our log laws, we can actually leave that out the front. And then I can simplify this. 7 on 21 is going to be 1 on 3. Now, I just want to point out something interesting here that we actually didn't necessarily need to do this step where I pulled it in. So just as a general rule for yourself, and this was kind of showing you, again, just like the previous question, showing you the steps of why that works. Now, in the future, if you've got the same value in the front, you actually don't need to pull it out. But if you're ever unsure, you feel free to, like you saw, I can just pull it back out. But I just wanted to show you the steps there. All right, now we're almost there in terms of simplifying. Now I'm at a point where I probably can write it as the same base and have a think about, can I write 1/3 as a base of 3? Which I should be able to, because that would just be 3 to the power of -1. So again, that -1 can come out the front, and log 3 will just turn into 1. So then 2 times -1 will be -2. So that's how I would simplify that equation there. Just add some equal signs just to make it very obvious where we're at. All right. So some more simplifications. So we've got log 316 and log 364. What can we do with this? Now, 16 and 64 both can't be written as a base of 3. They can be written as a base of 4, but I'm not sure if that's going to necessarily help. Let's give this a shot. I can pull the 2 out the front and the 2 out the front there. There we go. Sorry, that should be a 3. Now, hopefully you could recognize log 3/4, log 3/4. That's the same number. I might use the highlighter instead. And you have to think about the number log 3/4 is equal. It's just a number. It's a constant. So it's kind of like just saying the number 5, even though it's not equal to 5. So because it's the same, I can actually cancel them out. It's the exact same number. So they will divide through to give you 1. And so the answer to this should be 2/3. So I can't cancel it out here because it's not the same value. However, here it is literally the same value after I've pulled out these powers here. Okay, next one, part D. So we're getting a little bit trickier here. So we've got log 5 and then the 4th root of 1 on 625. So something to the power of 4 gives us 625. I do believe that's 5. 5 to the power of 4 gives you 625. That's actually quite straightforward because when I simplify that, that'll just be 1/5. Now, if I want to make that the same base, I'll just do that. And then log 5 will be 1. And we're left over with the -1. So that was a really nice and easy one there. Okay, next we've got example 10, solve the following equations for x. So very similar to what we were doing, but now we're actually solving. We've got 2 sides of the equation rather than 1. Now the idea is that you want to try to get the log, either the log looking the same on both sides, or you want to be able to use your little swappy rule. So the swappy rule is this, where I can take the log over. Alternatively, if I have like log base EA, equal to log EB, then that must mean that A is equal to B. So these are generally your two situations that you want to end up in. So either something like that, or we've got the two logs. Okay. So in this case, I can see that it's probably easier for me to get the two logs on the both sides together. The first thing I'm going to do is pull the two out. So remember, you can only subtract if there was a 2 also in the front. So if I pull it back into the log, then that means that I can now divide the 2. So remember, when you subtract 2 logs, you divide the 2 powers. And if you recognize, that's exactly the same as this situation. I've got a log E on both sides. That must mean that the insides must be equal to each other. It's kind of like when we were getting the same bases before. So that's x squared x minus 1 is equal to x minus 4. From here is just a bunch of algebra. So I'm going to take the x minus 1 over. We'll go ahead and expand. So x times x is x squared minus 4x minus x plus 4. We'll simplify that. We'll take everything over to one side. Really, if I take this x squared over, that will just cancel out. So you'll end up with 0 is equal to negative 5x plus 4. I'll take the 5x over to make it positive, and then I can divide both sides by 5. Okay, so it's just a bit of algebra, but this is the key part here, trying to make them equal to each other. Okay, there's actually a few ways we can approach this. So one way for this one is we can turn this 3 into a log, and I can see that I'm using base 2. So what I mean by that is that 3 is the same as saying 3 log 2, 2, because remember, log 2, 2 is just 1. And then I've got both logs, they're being added, I can put them together. Alternatively, I can take this over to that side, and then I can use my swappy rule. So I'll try one of them, and then maybe you can give it a go with the other one. So I might turn the 3 into the log. I'm not sure which one will be easier. Sometimes one is, sometimes the other is, but it's worth getting used to both situations anyway. All right, so remembering log 2, 2 is just 1. I haven't pulled it out of thin air. It's just literally like writing, 1 is equal to 5 divided by 5. Same thing. There's so many ways we can write the number 1. All right, so 2 logs are being, well, first of all, before I can do anything, I need to pull this 3 out. I might do it all in one step. So just remembering that the 3 becomes the power here. And because they're being added, I can multiply. So in the bracket, I'll have 3x times 2 to the power of 3, which is just 8. And it's log 2, x plus 2. Now this is great because, have a look, the 2 logs are the same. That means I can equate the insides. So that'll be 8 times 3, which is 24x, equals to x plus 2. Take everything to one side, and we can just divide both sides by 23. It does give us a bit of a weird answer. Hopefully I haven't made a mistake anywhere, but that would be the process for this question. Okay, next one. So, I mean, when I'm looking at this, I'm thinking of the 2 coming out the front as a power. It's probably the easiest way to do it. Slug EX, and probably just using the exact same technique of equating the 2. So because these 2 logs are being subtracted, then I can divide the 2 and have a look at that. So there's kind of like brackets there, and log E on both sides can equate the same. So you can see that it's kind of the same thing over and over. I'm just going to go ahead and expand at the same time, just to make my life a bit easier. I'll multiply the x over. 3x squared minus 3x. Take everything over to one side. Just because I want to keep everything positive, I'm going to move everything over to this side. So 3x squared minus x squared is 2x squared. Minus 3x minus another 4x is negative 7x minus 4. And we've ended up with a quadratic. Now, I've noticed I've gone a little bit messy. So let me fix this all up. Feel free to start solving your quadratic as I'm fixing my board up. Okay. Let's try to go a little bit neater. So I'm just going to rewrite this nicely, and we can go from there. All right, we want two numbers that multiply to give us 8 and add to give us -7. So that's probably going to be -8 and 1. It's non-modic, we'll split the two. Take out what's common. Factorize the x minus 4 out. And solve x equals 4, x equals -½ Now, I just want to draw your attention to the types of solutions that we just got. So we got x is equal to 4 and x is equal to ½ And we kind of just want to have a look, are these reasonable answers? Now, because we have over here x log ex, it means that I should be allowed to substitute either one of these numbers directly into this and the equation should remain defined. However, we know that log or that the domain for the log is only going to be x greater than 0. So I actually can't have a negative answer if I have a log ex somewhere in my equation. And I mean over here as well, so 3 minus 1, you can't, sorry, x minus 1. Although, yeah, so it'd be -½ minus another one. That will also result in a negative on the inside of that log, so a negative x value, if you will, for the domain, which is undefined. So just keep that in mind, that in this case, the only solution is x is equal to 4. Okay, next one. Now, because before I turned the 3 into a log, I might do the other way this time. I might actually take the log over and I'll show you how to use that swappy rule. Actually, sorry, now that I think about it a little bit, if you'll notice, it's a little bit more complicated than that. This 2 does not belong to the x. It actually is squaring the entire log. So I'm going to start by taking everything over to one side, and I'm going to see if you can recognize what might be going on in this situation. Have a look at the way I've just laid it out. Oops, pen's gone a little bit crazy there. Okay, now if it's not super obvious yet, there might be one more thing that I can do to help out. So that 5 is in the way. I'm going to bring that out the front. So that is attached to the x. That's why I can bring it. However, this 2 is not. It's squaring the entire log. That's why I can't bring it out the front. Okay, now I wonder if you can recognize 2, 1, 0. What does that sound like? So remember in our previous exercise when we looked at the exponentials, 2x, 1x, 0x was using the quadratic rule. This is the exact same idea, but it's now with logs. There's 2, 1, 0. So what we're going to do is the same technique. Let a equal, except this time we're going to let it equal to log 4x. And so once I replace all the log 4x's, look what I end up with. That's another log 4x, and then of course the 3 is just there. I've ended up with a beautiful looking quadratic that I can easily solve now. It's the same as your exponential, it's just about recognition. Okay, 2 times 3, so two numbers that multiply to give you -6 and add to give you positive, sorry, can't speak today, add to give you +5. So I'm looking at 6 and -1. We'll separate the two. So we can go minus, oh, well, actually, rather 6, +6, -1, -3. Pull out what's common. Pull out what's common. So then we'll end up with, I can factorize the a plus 3 out and the 2a minus 1. So that'll be a equals -3 and a is equal to ½ But I'm not solving for a, I'm solving for log 4x. So I can go ahead now and replace the a with log 4x. All right, now this is where we use our little swappy rule. We actually haven't really used that before. So we can take the 4 over as a base, take the 4 over as a base. So x is equal to 4 to the power of -3. X is equal to 4 to the power of ½ Now 4 to the power of 3 is 64, and then because it's negative, it'll be 1 on 64. And 4 to the power of a half is just the square root of 4, which is 2. So this one is a little bit tricky. And it's just a technique that you need to recognize. I think the key thing is like realizing the difference of the two squaring the entire log versus attached to the x. So they're two different things. In this case, I can pull it out. This case, it's attached to the actual log itself. So just be aware of that in the future so you don't accidentally just pull the two out, because if you did that, then that would not be correct for this situation. Example 11, if log 4p equals x, log 4q equals y, show that log 4, that whole thing equals 3 minus 3x plus 3y on 2. So quite a loaded question. It looks like it's going to be kind of tricky, but there's a real technique to this. So if you can recognize what we're trying to do is isolate log 4p and log 4q. If we can isolate those two, then I can easily substitute x and y, which is all that I have in my equation that I need to equate it to. Whilst there is quite a lot there in the inside of that log, the technique for this would be to separate it. Try to separate all of the values, and then we'll use the log laws, and you'll see how easily this simplifies. So what I'm going to do to start with is I'm just going to rewrite this with a little bit more details. So we have 64 times q squared on p cubed times q, and I'm just going to write that to the power of a half. Now, what I mean by those more details, I'm thinking of the fact that there's a times, divide, and a times. And the reason that I'm thinking that is because of our log laws. Remember, when you multiply, or when you have the two insides multiplied, so log mn, what you do is you add the two logs. That's how you can separate them. So I'm going to do exactly that. So I have log 4, pen's going crazy as normal, log 4 64. Now, because it's times q, I'm going to write plus log 4q squared. Now we're going to be dividing. So dividing means we subtract. So log 4p cubed. Now the thing to just be really careful of, I know this is times, but this is dividing this whole thing. So there's two ways you can do it. Probably the way that makes the most sense is to put a bracket. Then we can write the plus like that. But when you go to your next step, just don't forget to expand that negative in. Okay, so you can see that I've simplified it, and it already looks a lot more similar to those first couple of logs that they've given us, the ones that are equal to x and y. Now we're going to see if we can simplify this further. We're really trying to isolate this idea of log 4p, log 4q. Now, 64 can be written as 4 to the power of 3. So that's the first thing I'm going to do. And just remembering, because I'm going to just try to do it all in one step. Yes, this is 4 to the power of 3, but what I can do is take that 3 out the front straight away. So I'm just going to write that as 3 log 4 plus, again, taking the power out. So that'll be 2 log 4q minus, now the 3 out the front. And then don't forget to expand that negative in. So that'll be minus, and again, the half out the front. Okay, now the reason that I've done this is you can see that I've just got log 4q and p left over here. And of course, I've got a log 4, which just equals to 1. So wherever I see these, I'm now going to be able to substitute in my x's and y's. So log 4 is just 1, so that's 3, plus log 4q is y, log 4p is x, and log 4q is y again. And you can see how similar that looks to our answer. So I have a 3 minus 3x, and then 2y minus a half is going to be 3 on 2, which is exactly what was required. Okay, next few examples. So example 12, we've been exposed to this already. Hopefully you can recognize the 2x, 1x, no x, the idea that we're going to use the quadratics. I'm assuming that this example here is because we're going to end up needing to use logs in our final answer. So let's just complete it as we normally do. So the technique for this, remember, is to let a equal to e to the x. So that'll be a squared minus 8a plus 15. We need two numbers that multiply to give 15, add to give 8, that will be 5 and 3. So that will be a equals 5, a equals 3. Now we can go ahead and substitute EX in. Now, unlike the previous questions that we've tried, we can't just make the bases the same. So we actually have to take the base over to the other side using our log laws. So there will be a natural log of 5 and 3. Very similar with this question. So first I'm going to take everything over to one side. We'll let a equal e to the x. So it'll be 2a squared minus 9a minus 35. So this one might be a bit more tricky. We need two numbers that will multiply to give us negative 70 and add to give us negative 9. That will be negative 14 and 5. So it might take a little bit of time to just come up with those numbers. We will split the middle term because it's a non-monic polynomial. So that'll be negative 14a plus 5a minus 35. And then we will factorize by grouping. So I can take out 2a here, and I can take out 5 here. Then the common factor is a minus 7. So that will give us a equals 7, a equals to negative 5 on 2. Now, of course, we're just going to replace the a with an e to the x, and we're going to do the same thing with our logs. So taking the e to the other side, we do that by taking the log, the natural log. Now, if you'll notice, this is log of a negative number, which is not allowed. So logs are only defined for x greater than 0, because there's no number that we can put something to the power of that will equate in a negative. So this answer here is undefined. So the only answer we have is log E7. All right, so long exercise, one more concept. It's this concept of the change of base. So there's this really cool thing that we can do, which is actually change the base of a log, and it's quite useful in particular questions where you want the base to match. So this is the kind of proof for it, or the idea as to how we get that. So a to the y equals x. If we take the log b of both sides, so whatever you do to one side, you have to do to the other. You can take the power of y out the front, and then you can divide both sides by log b. So you can see that we've started off with a to the y equals x. So y equals log bx on log ba. Now, recalling that a to the y equals x implies y equals log ax, then we have log ax, because y equals log ax, equals log bx on log ba. Now that's the kind of proof. If that didn't really make too much sense, don't stress, have a look over it a little bit more. The key thing to remember is if you do want to change the base to whatever number you want it to be, usually we change it to the natural log, then the number on the outside is the top and the number on the inside is the bottom. And that's how we can change the base. So here it says evaluate each of these. Now we can see log 16(2). That doesn't really help us because usually we try to get these to be the same base. But maybe there's a number that will work for both of them. So the thing that I'm thinking of is a base 2. So using the rule, if I want to change these to a base 2, the top number or the outside number is the top. So you can put in any base you want, and then the inside number is the bottom. And that really helps because log 2 is 1, whereas log 16, remember 16 is 4 squared, oh sorry, 2, it is 4 squared. It's also 2 to the power of 4, and we want a base of 2, so that will just equal 4. Same thing here. So I'm thinking the number 3. So I just randomly choose 3. I mean, it's not random, but I can see that 3 is a factor of both of these. But as in I can choose any base that I want. Then we have the outside number and the inside number. Now log 3, 9. 9 can be written as 3 squared, so there will be a 2 left over, and 27 can be written as 3 cubed, so there will be 3 left over. Example 13, if p equals log 5x, find the following in terms of p. So this isn't necessarily change of base. When I look at these kind of questions, then what I'm thinking of is, well, first of all, I want to get rid of the x, and if I want it in terms of p, I need to kind of rearrange to get x by itself over here. So if p is equal to log 5x, then x, using the change or our log laws really, x would be equal to 5p. So in terms of x, that would be 5 to the power of p. Now, for this second one, log x 81, we want it in terms of p. What I'm thinking is that maybe we can use the change of base rule and change it to a base of 5 based on that's what it looks like it wants. So that would be the top number over the bottom number. And we know that log 5x is equal to p. Now, I'm not sure if that's exactly the kind of answer that we want. I mean, it's not wrong. It definitely says it's in terms of p. There's nothing wrong with that. I'm just wondering if there was a better way to be able to simplify that. So maybe you can come up with something that looks a little bit better than that. But otherwise, I mean, this is a totally valid answer. It's in terms of p. I've been able to replace the x. So the idea is that I've found a number that looks like that I can then replace it with p.